Hi, everyone. Thank you for taking the time to listen to this talk. Today, I want to talk about some work done with Karthik Gopalakrishnan, Hamsa Balakrishnan, and Lavanya Marla, where we look at the dynamics of kind of how networks, in particular airline networks, can be disrupted and also how they recover. And what I want to go through today is first to set up the background and motivation for the problem, talk about what I mean when I think about constructing these kind of disruption recovery trajectories, investigate some of the properties of these so-called DRTs, and then look at one application of clustering DRTs, which can reveal some common patterns of disruptions and recoveries within the US airspace. And then I'll finally conclude with some future work. So to start off with the background and motivation, what I want to start with is this clip that I'll set up for you right now. What you'll see are basically expanding circles around major airports in the US. The larger the circle, the redder the circle, the more delays there are at that airport. So in particular, this is kind of a 12-hour period where a large convective weather system kind of moves through New York, followed by another line of pop-up thunderstorms. I'll play this again. You'll see the delays kind of increasing at the New York airports before finally kind of settling down. So when we look at a 12-hour chain like this, a natural question is, how did I pick the 12 hours? When did this disruption chain start? And when did it start to recover? When did the system begin to recover? And between the beginning of the disruption and the end of the recovery, what are the characteristics of this particular disruption and recovery cycle? So these are kind of hard questions to ask because there are some more straightforward answers, like what if you just monitor the total delay or cancellations at the airport, or you can base it off of the forecasted weather. But the issue is, are they complete answers? So does that tell you everything we need to know about a particular series of disruptions or the subsequent recoveries? Can we do better? Can we have a more formal framework for how to spot, organize, and classify these kind of disruption recovery cycles? And can we ask for some properties of it that we might want? So for example, maybe we want our classification to also consider not only how much delay, but what the geographic extent of the delays are in the system. And also we would like it to be kind of backwards compatible with some usual notions of airspace delays that we might have used to kind of give a more straightforward answer in terms of classifying and identifying disruption and recovery cycles. So, to survey some past work that is kind of the most relevant to this work, you can look at certain, passenger and crew recovery work, which is more of disruptions and recovery at a microscopic level. You can also zoom out and look at a more broadly focused on kind of disruptions in network systems. And this is kind of the step that's a little bit closer to what we're trying to do here, except we're also trying to build a framework that actually depicts these cycles of disruptions and recoveries. And also, there's been a lot of work done on looking at very specific events and how to recover from those specific events. But there's really been no kind of comprehensive framework for how to actually classify and identify broad generic disruption recovery trends that are more or less agnostic to the actual cause. So now, the idea, the concept that we'll use are what we're going to call disruption recovery trajectories, or DRTs. And I'm going to go through how to construct one of these objects that we'll be working with. So to start, the airspace, the air transportation system is a very complex system. And perhaps we just want to measure certain aggregate performance measures of this particular system. So what I mean by that is, suppose so up above, you have basically the entire airspace evolving and the delays are evolving on an hour by hour basis. This is what I'm going to call the state of the system. What we might want to do is just look at aggregate performance measures So for example, perhaps we can examine how much delay there are in the system. This is a pretty canonical measure of what the disruption, how severe the disruption is in my system. And then we've done a lot of previous work to use this particular metric called the total variation metric, which gives you a sense of how geographically dispersed or how spread out the delays are in your system. So suppose we take these two aggregate performance metrics, and what we're going to do is we're going to take the state of the system and project the state onto this lower dimensional performance space. So suppose, each of these states are labeled A through E. For each hour label, we can compute the total delay, sum of the delay in the system. We can also compute the total variation, which is a slightly less trivial computation. I would be happy to answer questions about that later. But essentially, the total variation is you take the delays in the system and kind of manipulate it using underlying connectivity and graph structures that you've built in. So once you projected these down onto your low dimensional performance measure, you're going to get basically the scatter plot. So this is an actual example for Southwest network, and I've just plotted these 5 projected states onto my lower dimensional performance space. What I'm now going to do is let's connect consecutive states into a trajectory. And as I've mentioned before, I'm using discretizations of 1 hour. So for each state, it's like 8 a.m., 9 a.m., 10 a.m., etc. Let's connect consecutive ones into an object that I'm going to call as the trajectory of the system in this lower dimensional performance space. So this is an example of what one of these trajectories look like. And as you can imagine, you can have trajectories that span hours, days, months. You can construct an entire trajectory and now start looking at chunks in the trajectory where certain disruptions and or recoveries happen. So in particular, what we can do now is to try to extract from a larger trajectory object these individual disruption recovery trajectories, or DRTs. And what we can now do, now that we have these tangible objects that tell us something about how the system is being disrupted and how the system is recovering, we can do things like clustering, prediction, and control on these objects. And immediately, there should already be kind of a vague sense of where you might want to ideally be on this space. For example, this corner is a pretty obvious choice, because in this corner, not only are your delays low in the system, but also they're not spread out in some crazy way. But the other areas are a bit more vague in terms of classifying if they're good or bad. What we've done is, and in the reference in the back of that I'll show at the end of these slides, we've done what's called this decomposition or partitioning of this space into different areas, where the first area kind of represents basically low delays in your system, where your system is pretty operating quite nominally. This is one example of one of these one states of what your system might look like. Another, here in this area, your delays are very high, but your delays are high uniformly through your system. So the delays are high, but the spatial dispersion is quite low. Another partition might be this one, where your delays are the total delays in your system is low, but the spatial distribution is very abnormally distributed. So in this case here, we see that the total delay across the system is pretty low, but there is a large delay spike around at Ronald Reagan National Airport, but it's not very well dispersed. It's very concentrated at a particular airport. So these kind of realizations of your system state will appear in kind of the 3-state area. And then finally, the 4th state is where everything is out of whack. So your delays are extremely high, and they are also very wildly dispersed in your system. And now what we can do is we can think about classes of trajectories that traverse between these individual states. So for example, a trajectory that we call a disruption trajectory in scale is going to traverse between low and high total delay, whereas a disruption in spatial distribution is going to traverse between kind of the zone of nominal spatial distribution and zone of not nominal spatial distribution. And then we can also have a sense of what an integrated disruption is, where anytime you leave this nice nominal one zone, you're going to be considered as part of a disruption. And these DRT objects, these kind of discrete transitions between states, it turns out that they have some pretty nice properties that I'm just going to state here without proof for the interest of time. So what we see is that the scale and distribution DRTs, you can always turn them into an integrated DRT and vice versa. So integrated DRTs, you can always decompose them very nicely back into scale and distribution DRTs. So this really ensures that we have kind of forward and backward compatibility between our disruption definitions, and also that this integrated DRT is indeed kind of a complete closure. It kind of encompasses all other DRT definitions. So we've really satisfied kind of the three conditions that we laid out in the beginning in terms of what we would consider to be a good definition of disruptions. So finally, I wanted to take this last part to talk about clustering. So clustering, of course, starts out with features. The features on the left-hand side are more self-explanatory: how long a trajectory is, how long you stay in each state, and what the maximum observed total delay and total variation you see along the course of that trajectory. The ones on the right-hand side, I'm going to go through a little bit more in detail. When we say average intensity, what we mean is you have a DRT. What is the kind of the average total delay normalized by the maximum total delay, or the same can be computed for total variation. So this gives you a sense of how intense your DRT was. How was your DRT, was your delay, was your disruption and recovery mostly at the extreme end, or was it a pretty meandering disruption and recovery? We also have this notion of area. So what we mean is when we look at a trajectory that we can draw out, we can actually compute the area underneath the trajectory in order to figure out, was the total variation higher or lower on the disruption or recovery phase? So was the kind of the geographic variance in your system higher on the delay, on the disrupt when your system was being disrupted, or was it higher when it was recovering? And then finally, we have these what's called symbiotic and trade-off segments. If you can imagine, you have when you look at a point on this space, depending on which direction you move when you evolve into the next state, you're either going to be increasing and decreasing in both delay and total variation, or you might have a more trade-off maneuver, or maybe you're increasing delay at the cost, you're increasing delay, but you're able to decrease your total variation, or you're decreasing your total variation at the cost of increasing your total delay. So these kind of physical attributes for these trajectories, we can turn into clustering features and do clustering to identify representative DRTs. So the data set that we used was from the FAA ASPM database. We looked at a 10-year span discretized into hours for the top 30 airports in the US. And what we find is that we can classify these disruptions quite clearly. We have one class that are your shorter disruptions, 3 to 4 hours on average, and very high intensity during these 3 to 4 hours. More medium disruption recoveries, which are around 6 hours on average. And then the last two classes are your much longer disruption recovery. So some of them can take up basically your entire operational day, 15 to 18 hours-ish, or they can actually last for days on end. So these multi-day disruption recoveries usually are averaging 55 hours. And this shows that during these severe disruptions, your system wasn't even able to recover during periods of more inactivity where you might have less scheduled traffic. So this is an extremely rare, but also extremely impactful disruption and recovery cycle within the US airspace. So to conclude, here what we've done is we've tried to use this kind of state space trajectory representation to come up with a formal framework for disruptions and recoveries within air transportation networks. We've shown that you're able to prove some nice properties about them, as well as use this framework to classify different kinds of disruptions and recoveries. And in terms of ongoing work, the most interesting avenue is now that you have this tangible object, you can ask interesting prediction questions such as, if you're not part of a DRT, when will you become part of a DRT given current weather situations, et cetera? Or the dual, which is you currently are part of a DRT, when will you recover? When will you finish your disruption and recovery cycle? And this really also leads into interesting questions regarding control and controlling the progression of a DRT.